Hey guys, welcome to the 5.1 notes, simplifying radicals and end roots. So first of all, we're going to talk about perfect squares. So like 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared. There are other numbers squared, but we're just going to go ahead and go up from 1 through 10. First of all, 1 squared is just 1. 2 squared is 4, 3 squared is 9, 16, 25, 36, 49, 64, 81, 100. I'll give you guys a second to go ahead and write these down. While you do that, I will kind of explain the whole reason why we're doing this is because we're going to be doing some square roots. And in order to get rid of a square root, you need a squared power. So square roots and these powers of 2 cancel each other out. Just like cubes or powers of 3 and cube roots cancel each other out. Now we're going to do some powers of 3 also. Pause the video if you need more time on the squares. So 2 cubed is 2 times 2 times 2 again. So basically 2 squared times 2 again is 8. 3 cubed is 3 squared, 9 times 3 again, 27. 4 cubed is 16 times 4 again, 64. 5 cubed is 25 times 5. 5 quarters will be $1.25 or 125 cents. 6 cubed. This one gets a little bit trickier. Will be 36 times 6, which is 216. And then I'm actually going to go all the way up to 8 and stop there. So 7 cubed is 49 times 7 again. This is 543. Sorry, blanked for a second. And then 8 cubed is 64 times 8 again, which is, I don't remember this one, so I'm going to have to do it real quick. 512. I remembered my 7 cubed wrong. Let me double check for you. Yeah, this one should be 343, not 543. Okay, I'll give you a second to get those written down. Well, I explained that these are there to undo cube roots, which is like a square root with a little 3. And fourth roots are here to undo fourth roots or fourth powers. Okay, so I'm only going to go up to 6 on this one because at 6 it starts getting a little out of hand. We're taking this times 2 again, which is 16. We would be taking 27 times 3 again, which would be 81. 4 to the 4th is 64 times 4 again, which is 256. 5 to the 4th power would be 125 times 5 again, which should be 625. Sorry, 125 times 5 again. Yep, 625. And then 216 times 6 again is 1,296, which is why I'm stopping there. Notice how these are a little bit higher and they go a little bit more out of hand because you're doing something to the power of 4. Okay. And we are going to be simplifying using these numbers. That's why I want you to have this list. Please do me a favor and make sure this says 343 on it. Okay, so here is what a radical looks like. This weird symbol right here that kind of looks like a heartbeat, that is the radical itself. The word radical is referring to that symbol. The number in the little corner right here, notice how this isn't out front. It's almost like an exponent, but it's in this little V part of the radical sign. That is called the index. And it tells you which power you're trying to undo. Okay? And then the number inside is called the radicand. So the radical is the symbol and the radicand is the part on the inside. then we're going to talk about just some patterns really quick. If your index is even or odd. And I'll give you some examples. While the possibilities are limitless, evens are going to be pretty much 2 and 4 for us. Odds are going to be 3 and 5. We're actually not even going to really do fifth roots. We're only going to do 2, 3, and 4, but it's on there just in case. So these could technically go higher, but I'm not going to have us go there quite yet. Okay. So the radicand, or the inside. Here we're going to write whether it's positive or negative. If you are trying to take an even root of a positive number, like let's say the square root of 25, you technically could have two answers. And these are both real answers because you need a plus and minus. So the answer to this could have been 5 or negative 5 last unit. If you want to take the square root of a negative number, you should know that that's normally not possible. We would call those answers imaginary. In this case, it would be like 5 and negative 5i. We're not going to deal with any of those now. If you have been ready to get rid of I for a little bit, that's going to be in this unit. And then we have our odd ones. So this would be like trying to take the cube root of 8, picking one of our numbers from our perfect cubes list. This is going to be one answer, positive. If you take the cube root of negative 8, that's actually okay. You're going to have one answer, negative. So it's going to match whatever it is on the inside. You can put whatever you want inside an odd root because the only reason why you can't take the square root of negative 25 is because there's two negatives, which always multiplies to a positive. 3 negatives can either be, you can either have a positive or a negative, 3 negatives or 3 positives, and then you have one of each type. So you actually can take the odd root of a negative. The cube root of negative 8 is negative 2. It exists. It's not imaginary. So it's only okay to take the square root of, or the negative root if it's odd. As we write our answers, though, for this one up here, we are only going to write the positive one unless we are solving an equation that has x squared in it. The only time you have to do this is if you're using the square root to cancel out the squared. All right, so here we have the square root of 121. I'm only going to do this over here because I want to show you why we do this. Basically, you're looking for something to the power of 2 to cancel out the square root. Okay? If there is no number in front, assume it is automatically a 2 for the square root. Then I basically am asking myself, what number squared is 121? It's not on our list, but it's 11. So then the square root and the squared cancel each other out, and you just have 11 as your answer. Okay, same thing's going to happen over here, except for I'm going to do the square root of 4 on the top and the square root of 25 on the bottom. These are the same thing. Square root of 4 is 2, because 2 times 2 is 4, and the square root of 25 is 5. You can also use this list that we made to figure out what number squared was the one you're looking for. And even though this is a fraction, you are actually done with it right here. There you go. And then we're going to come over here. Now that we are in the cube roots, I need to make sure that I'm looking at the cube roots. So these numbers. Not these, because I'm not a square root anymore. I have a cube root, so I'm looking for these, which would be 7. The one that I messed up earlier. And then we're going to do the same thing on the last one, except for now I'm in the fourth roots. So I need to go figure out where 81 is on my fourth roots list. That's 3. Okay. And 16 is 2. There you go. That's if they work out nicely. Bottom row is going to be what happens if they don't work out nicely. So like right here, we have 320. We want to split this up into two numbers that multiply to 320. Now, we need to pick from our perfect squares list. Okay? So I'm going to take my calculator out and I'm referring up to my perfect squares, which starts with 4. That goes in 80 times. There's still more things left in this other number, so I need to go bigger. Doesn't even work. I have 20 left. There are still a lot of numbers that go into 20, some of which are perfect squares, so I'm going to keep going. And it seems like I'm out of options for a little bit, but then I try 49, 64, and I get 5. So I'm just going down my list of perfect squares, guys. Now, 5 does not have any other numbers that go into it. That is what you want. And the square root of 64 is 8. So that 8 gets to come outside, but the 5 has to stay underneath because there is no square root of 5. It only gets to come outside if you can do the square root. And then this 4 is still out there. What happens is it gets multiplied. So if there are any numbers outside together, they get multiplied together. 8 times 4 is 32. So we have 32 square roots of 5 as our answer. And then I'm going to do the same idea over here, but with 108 as my starting number. And this time I'm going down my list of perfect cubes. So I can try 8. Nope. 27. Perfect. It's 27 and 4. Now, here's the part where some people get a little confused. This 3 is just going to stay out there for a second. The cube root of 27 is 3 on our list. But the cube root of 4 doesn't exist. Some people think they're doing the square root again, and so they'll change it to 2. But you can't do that because it's not the square root, it's the cube root. And then outside, 3 times 3 is 9. I call this the Harry Potter problem because it looks like 9 3/4, but it's not. Okay, and then the last one, or the second cube root one, sorry, we're going to take 250. Okay, and I'm actually just going to go ahead and take negative 250 divided by my perfect cubes, 8. Doesn't work. I'm getting tired of writing the negative, so I'm not going to. 27 doesn't work. 64 doesn't work. 125, perfect. It's 125 times 2. And I'm going to go ahead and leave that negative in front where it is. And then the cube root of 125 is 5. That's from up above. And you can just take the negative with it. The 2 has to stay underneath because it doesn't have a cube root. And I would just put the negative in front. That's the place where it's easiest to see. So that's why I wouldn't leave it in the middle like this. It's not technically wrong. It just makes it a little bit easier to see it. And then I'm going to come over here to my last one on this side of the page. And I'm going to try finding a perfect 4th power that goes into 162, which starts with 16. Doesn't work. Then it goes to 81. Perfect. So this is 81 times 2. And in case you haven't been sure about what in the world I'm doing, the cube root of 81 is 3, or 4th root of 81 is 3, because 3 to the 4th power is 81. So just the same way I was showing you these squares cross out, this is really 3 to the 4th power, so the 4th power and the 4 cancel out, and now this is just 3. This 3 stays, and you have the 4th root of 2 left. Okay, so I'm going to get 9 4th root of 2. And I forgot to box my answer over here, so I'll go ahead and do that now. And then we're going to talk about how variables work on the back side. All right, so for a square root, you can actually cancel out exponents in multiples of 2. Cube root in 3s, and fourth root in fours. I'll explain what that means up above. I'm going to do an extra problem right here in the margin. I'm going to use a cube root as my example. X to the 12th power. Like I said on the front side, that means that you need something inside here to the power of 3 if you want these to cancel out. If I were to put an x in here, whatever exponent I put here gets multiplied by that 3. So these two exponents will always multiply. So really, I'm asking myself, what times 3 equals 12? Well, 4. And then these cross out, so I have x to the 4th left. So what I'm really doing is trying to figure out how many times this goes into this. And sometimes there will be a little left over, and I'll show you how to work with that. Okay, coming right here, I'm going to do my first example. So I'm going to start with 32. This is a square root, and I can divide 32 by 4. Goes in 8 times, but 8 still has other numbers that go into it. So I'm going to keep going. 16 and 2. 2 doesn't have any other numbers that go into it. So right now I'm going to split this up into 16 times 2. And then the square root of 16 is 4. So a 4 gets to come out. And a 2 has to stay underneath. Now I'm leaving a little bit of a gap so I can do the numbers. Remember that a square root has that imaginary 2 right here. Well, 2 goes into 4 twice. So that means x squared gets to come out here. There's none left in here because it went in evenly. 2 goes into 9 4 times, because 2 times 4 is 8. But it has a leftover of 1. So whatever the remainder is, stays inside the square root. So I have 4x squared y to the 4th times the square root of 2y. Okay, over here with 324, I want to show you what happens with 324 when we try to divide it. So it does go into 4. We've got 4 and 81. So something interesting that happens with this one is those are both perfect squares. That means that 324 is a perfect square. We just didn't include it on our list, and that's okay, because that means that square root of 4 is 2, and the square root of 81 is 9. They both get to go outside because they're both perfect squares. Then 2 goes into 3 once, so 8 of the first comes outside, and it has a leftover of 1, so 8 of the first has to stay on the inside. 2 goes into 7 3 times, with a remainder of 1, so 1 has to stay inside. Again, these are your remainders. 2 times 9 is 18, a, b to the 3rd, square root of a, b. Be careful that you don't get this mushed together with your radical, because it's a square root, not a cube root. And sometimes you can make it look like one. All right, now we're getting into a cube root. So 216 is on our list of perfect cubes. The cube root of 216 is 6. Then 3 goes into 3 once. So m to the first comes outside, and you don't need to have anything left inside. 3 goes into 6 twice, so we have n squared. Nothing stays on the inside. So on this one, sorry, that should have been a cube root, nothing's left over here. So it's just 6m n squared. Okay, next one. Cube root of 56 r to the 8th s to the 4th. 56. I'm going to try dividing by my perfect cubes. And there we go. I have it on my first try. It is 8 times 7. The cube root of 8 is 2. There is no cube root of 7, so it has to stay underneath. 3 goes into 8 twice, so our 2 comes out. And that would be 6, leaving me with a remainder of 2 to get to 8. So I have 2 left inside as well. 3 goes into 4 once, and it has a remainder of 1. So I have 2r squared s times the cube root of 7r squared s. And sometimes what some people will do to help them see the difference between the radical and this, so they don't think this is s to the third, is they'll put a multiplication dot right there, if you're having trouble reading your handwriting. Okay, I'm going to zoom through this next one a little quicker. 81 is on our perfect squares. 81 is not on our perfect cubes list. So 81 divided by 8, nope. 81 divided by 27, yes. Again, these are off of our perfect cubes list on the front page. Okay, negative 27 times 3. The cube root of negative 27 is negative 3. There is no cube root of 3, ironically, even though they're both 3s, so it stays underneath. Then 3 does not go into 2 at all, so both the whole p squared has to stay underneath. Nothing gets to come out. But then 3 goes into 12 4 times, so I can put q to the 4th out here. And there you go. Negative 3 q to the 4th, cube root of 3p squared. And then I'm only going to do one of these next two just to keep things a little bit shorter. I'm going to do this one. So 48 is not a perfect fourth root, so I'm going to try dividing it by ones that are. Like 16 is our first one. There we go. 16 times 3. Hang on, sorry. Then I need to do the fourth root. Fourth root of 16 is 2. There is no fourth root of 3, so it has to stay underneath. 4 goes into 8 twice. And 4 goes into, there's no remainder, so there's no m's left under here. 4 goes into 3 no times, so the whole n cubed is left underneath. Leaving me with 2m squared times the fourth root of 3n cubed. Okay, and then I'm going to skip this one, but I'll show you the answer at the very end if you would like. I'm going to move on to the last one. On this one, don't worry about what's in the middle for a second. 4 goes into 8 twice, so this would really be the same thing as y plus 3 squared. The same way we put the exponents outside like this, there's just a y and a plus 3 inside. As long as it's in parentheses, you can do this. Then we're going to answer this all the way. We need to square y plus 3, which means we're doing y plus 3 times y plus 3, which gives us y squared plus 3y plus 3y plus 9, or y squared plus 6y plus 9. If you're curious as to the answer to the one before it, it should have been 5c to the 5th d squared times the fourth root of c to the 3rd d to the 3rd.